In this video, we are going to talk about the kinematic equations, which are three equations that we use to describe the motion of objects undergoing constant acceleration. So these equations here are our three kinematic equations, and in this video we are going to derive them from our known relations between acceleration and velocity and between velocity and position. So these were discussed in the last kinematics video, so you should already be familiar with those. If you're not, go back and watch that video. So the first thing that we are going to do is we're going to derive this first kinematic equation, which relates the final velocity of an object to its initial velocity and its acceleration. Now, the first thing you should notice is that I haven't put vector signs on these velocities and accelerations, where here my velocities and accelerations are vectors. So in order to make the math more technically correct, we are going to deal with only the magnitudes of these vectors. So for example, you could think about having this acceleration deal with just the x direction. So I could say that my acceleration looks like some magnitude of acceleration in the x direction. And likewise, I could say that my velocity looks like some magnitude of velocity also in the I hat or x direction. So then if a vector, if I rewrite this equation here, in terms of this, I would write a times I hat equals dv dt times I hat, where I'm just acting the derivative on the magnitude of the velocity here. And if you are familiar with calculus and you say, oh, but I should act the derivative on the I hat component here as well. Well, the I hat vector, the unit vector I hat doesn't change, so it doesn't have a derivative. So we don't need to worry about that derivative. In any case, we can now say, well, look, I have some value multiplied by I hat equal to some other value multiplied by I hat. So these two things in front of my I hat, my direction unit vector, must be the same. So we get this a equals dv dt. And so now we have an equation that doesn't have these I hats running around, and it makes our life a little bit easier as we try to do calculus and multiplication and division on these, because we're not dealing with the full vectors here. And in the end, what we're going to find is that these equations apply individually for, say, the x direction, and then the y direction and the z direction if we're working in 3 dimensions. So for example, I can write down my final velocity in the x direction, say left and right, in terms of my initial velocity and acceleration in just the x direction. And if I wanted to work in the y direction, I could use this exact same equation, but in the y direction, to find out about my velocity in the y direction as well, where I would just use y values for velocity and acceleration instead of x values. Okay. So what we are going to do is we are going to use my scalar relation. Scalar, remember, just means that I'm dealing with only a magnitude with no direction. A equals dv dt. So I'm going to do something which is called separation of variables, which means simply that I put all of the stuff that dt depends on one side and all of the stuff that dv depends on the other side. Now, the only thing that depends on dt is dt, and the only thing that depends on v is dv. So this was quite easy. And the nice thing about this is now I can integrate both sides. So I have this relation, a times dt equals dv, and then I just integrate, and I just need to make sure that I integrate these two things over the same interval. So let's say that I start at some time t initial. That is the time when I start my stopwatch. And we are in general, though not always going to set that equal to 0. So I'm going to integrate from some initial time to some final time over dt. And I'm going to have to integrate my velocity over the equivalent time span. So I'm going to integrate from some v initial, that is the velocity at time t initial equals 0. So this velocity happened at this time, to some v final, whereby v final happens at time t final. So it could be that I start my stopwatch and I have I'm moving at 3 meters per second, and then I stop my stopwatch 5 seconds later, and 5 seconds later I have some other velocity, 10 meters per second, say. Okay, well, this right side integral is quite easy. It is just v, from v initial to v final. And here is the part where I rely on the fact that the acceleration is constant. So the equations that I wrote down at the beginning, our 3 kinematic equations, work only for constant acceleration. And if the acceleration is constant, it doesn't depend on time, and I can rewrite this integral as a times integral of dt. Because if this doesn't change, it doesn't need to be inside of my integral, which is great because now I can write this as a times t from t initial to t final, and plugging this in, I get v final minus v initial. So when I plug that in, I get v final minus v initial equals a times t from t final minus, or from t initial equals 0 to t final. Plugging this in, I get a times t final minus a times 0 equals v final minus v initial. And now I'm going to let t final just equal t. Because I don't have a t initial, I can just say, well, I'll integrate from 0 to time t. And so all of the textbooks and things, they don't write t final in general. They will just write t. And plugging this in here and rearranging, I get v final equals v initial plus at. So this is my first kinematic equation. I'll write it here. And to find it, all I did was take my definition of acceleration, that is the change in velocity per time, and I integrated both sides after separating my dt and dv. And I explicitly relied on a equaling a constant such that it doesn't depend on time, so that I could pull it out. So this is the step that requires my acceleration to be constant. If my acceleration is not constant, nothing after this line works. I can't do any of this if my acceleration isn't constant. Fortunately for us in this class, we're always going to deal with constant acceleration, so we don't have to worry about that. But the next equation that we're going to do is we are going to take this result and use it on our definition of velocity. So we know that velocity equals the derivative of position with respect to time. And we're going to use the same idea to say that my velocity is dx dt. The same idea as we did for the acceleration, where we're going to say, okay, well, let's imagine that these both point in the x direction. And then I can say, well, my velocity in the x direction must equal my rate of change in the x direction. And I can kind of cancel out the unit vectors, the I-hats. Okay, so we're going to use the scalar equation that relates the magnitude of my velocity to my displacement in the x direction. And now I'm going to use the same trick again to say that v dt equals dx. And I can integrate both sides. I will integrate this from, again, t initial equals 0 to some t final. And I'll integrate this from some x initial to some x final, where x initial lines up with the location of whatever object we're keeping track of at t equals 0, and x final lines up with the location of whatever object we're keeping track of at time t final. Okay. Now, our velocity, we are allowing to change. We are keeping our acceleration constant, but velocity can change because acceleration by definition is the change in velocity, and we're not requiring acceleration to be 0. So I need to plug in the value of my velocity at any given moment, which is given by this equation here. This is my velocity at some time t. So what I need to do is I'm going to say that this is the integral of v initial plus at dt integral of dx. And I'll put my limits of integration in. Okay. So, acceleration can't change, it's a constant. V initial is the velocity that you started with, and that doesn't change over time. It's whatever, when I started my stopwatch, that object had some velocity. Maybe it was 5 meters per second, right? That hasn't changed. 10 seconds later, the time that the object had when I started my stopwatch is still 5 meters per second, right? So you have some velocity that you started with, and you have some acceleration. The only thing that depends on time here is t. And taking this integral, I get v initial times t plus 1/2 a t squared. And I evaluate it from 0 to t final. And the integral of dx is just x evaluated from x initial to x final. So plugging in here, and once again, I'm going to let t final just equal t. I get v final t plus 1/2 a t squared equals x final minus x initial, or rearranging, I get x final equals x initial plus v initial t plus 1/2 a t squared, which is my second kinematic equation. So again, I did exactly the same trick. I started with my velocity relationship written in terms of scalars. I then separated my variables and integrated both sides from some initial time to some final time. And I then just took the integral, knowing that my initial velocity and acceleration were simply constants, and I solved and I got this. Now, this equation, I didn't specify really a direction here, so this equation could apply to objects moving in the x direction, could apply to objects moving in the y direction, it could apply to objects moving in some combination of those directions. You just have to pick an axis along which you want to use this equation. But this doesn't only hold in the x direction. Okay, now the final equation, the final kinematic equation, simply comes from taking this equation and plugging it into this equation. So our final kinematic equation is v final squared equals v initial squared plus 2a delta x, which is just the final position minus the initial position. Delta x is always the final value of whatever is being deltaed, so the final value of x here minus the initial value of x. To get this equation, all you do is you take this equation here and you solve it for time. So if I solve this for time, I get v final minus v initial divided by the acceleration. And then everywhere there's a time in this equation, I replace it with this. And when you do out the algebra, it takes 3 or 4 steps, but it's not super complicated. You end up finding this relationship from it. So it's just algebra, and this equation here is really just the other 2 equations put together.